Okay, suppose that the charge density or the potential has been specified over the boundaries of some region. And what we want to do is to find the potential at the inside. Now what we can do is we can solve Laplace's equation using a technique called separation of variables. And we do this, we're looking for a solution that is a product of the functions, each of which depends on only one coordinate. So let's just write up Laplace's equation again. So it's going to be equal to 0. I'm going to look for solutions of the form where v of x, y, z is equal to x that depends on x, some function y that depends on y only, some function z that depends on z only. Okay, so what we're going to do is we're doing this in Cartesian coordinates initially, and we substitute this then into Laplace's equation, and when we do this, what we get is we get an expression of the form here. So now what we've done is we've converted a partial differential equation into an ordinary differential equation. So now what we're going to do is we divide across by x, y, z. And when we divide across by x, y, z, what we're going to obtain is a term that depends on x only, a term that depends on y only, and a term that depends on z only. These are equal to 0. Okay, so we have three terms. First depends on x, second depends on y, and the third one depends on z only. Now, since these terms are going to add up to 0, each of these is going to be equal to a constant. Okay, so what we will have here now is we can write d2x is going to be equal to some constant that's called c1 by x. For y, we're going to have d2y over dy2 is equal to c2y. And for z, we have d2z over d squared c3 by z. And this is now where we have c1 plus c2 c3 equals 0. So what we've just done is we've separated the variables, and now we must solve for these constants so that we determine what x, y, and z are so that we can obtain our solution.